I'm so glad you found your way here. Right now, beneath your feet, Earth's crust is moving, just a few inches each year, building pressure that will one day release as earthquakes, eruptions, or mountain ranges. Tonight, you'll discover how destruction creates the world we know, and by the end, you'll understand why chaos and creation are the same patient process. Welcome to Sleepless Science Night. Wherever you are right now, perhaps feeling the solid ground beneath you, or simply resting in the stillness of night, allow yourself to notice Earth's quiet power. We'll explore 100 nature facts about geological transformation, from tectonic plates grinding slowly beneath oceans, to volcanic systems building islands grain by grain, to the moment when pressure becomes motion and stillness becomes change. These calm explorations of Earth's wisdom plant seeds of tranquility in restless hearts. Feel free to like and subscribe or share a thought down in the comments. Sharing this gentle science creates a pathway for more nature lovers to discover this healing ground, one sleepy soul at a time. Your presence here nurtures our growing forest of peace. Sink into your favorite resting spot. Allow your muscles to release, each breath growing softer. There's no need to remember these geological facts. Just notice that warm, drowsy calm washing over you, like gentle ocean waves pulling back from shore, each one drawing you deeper into restful, effortless sleep. Close your eyes and breathe deeply. You're resting where ancient trees whisper secrets of eternal wisdom. Let your mind sink with nature's calm. And now we begin. Earth's surface is broken into massive puzzle pieces that never stop moving. These tectonic plates drift across the planet at roughly the same speed your fingernails grow, about 2 inches per year. While that sounds impossibly slow, over millions of years these tiny movements reshape entire continents. The Pacific plate slides northwest, carrying Hawaii with it. The North American plate drifts west, creating the San Andreas Fault, where it grinds past the Pacific plate. Right now, as you rest here, India continues pushing into Asia, building the Himalayas higher with each passing year. This constant motion creates what we call natural disasters. Earthquakes when plates suddenly slip. Volcanoes where plates dive beneath one another. Mountains where they collide. But from Earth's perspective, measured across geological time, these aren't disasters at all. They're simply how our planet breathes and reshapes itself. Earthquakes release energy that has been building for decades or even centuries. Along fault lines, tectonic plates press against each other, locked by friction. Stress accumulates slowly, invisibly, deep underground. When the stress finally exceeds the friction holding the plates together, they slip, sometimes just a few feet, sometimes 30 feet or more in a single moment. The July 2025 earthquake near Russia's Kamchatka Peninsula registered magnitude 8.8, becoming one of the strongest earthquakes recorded this century. It ruptured a fault stretching nearly 300 miles and sent tsunami warnings across the Pacific Ocean. Yet even this immense release of energy represents just a tiny adjustment in Earth's crust. The plates continue their patient journey, already beginning to build stress for the next inevitable release, decades or centuries from now. Volcanic eruptions create new land while seeming to destroy the old. Iceland sits atop the mid-Atlantic ridge, where two tectonic plates slowly pull apart. Magma rises through the gap, building the island higher with each eruption. Between December 2023 and August 2025, Iceland's Reykjanes Peninsula experienced 9 separate eruptions along the Sundhnúkur crater row. Each eruption added new lava to the landscape, creating roughly 3 square miles of fresh volcanic rock. The town of Grindavik was evacuated multiple times, not because the eruptions were unusually dangerous, but because lava flows slowly, predictably, toward human settlements. From a geological perspective, Iceland is simply growing. The island gains new territory with each volcanic breath, expanding its footprint in the North Atlantic by a few acres at a time. Tsunamis demonstrate how Earth's movements ripple through water. When an underwater earthquake suddenly lifts or drops a section of seafloor, the entire water column above it moves in response. This displaced water spreads outward in all directions, creating waves that can travel across oceans at speeds exceeding 500 miles per hour. In deep water, these waves are barely noticeable, perhaps only a foot or two high, spread over hundreds of miles. But as they approach shallow coastlines, the waves slow down, compress, and rise dramatically. The July 2025 Kamchatka earthquake generated tsunami waves reaching 16 feet high in some coastal areas of Russia. Yet the same waves arrived in Hawaii and Alaska, measuring just a few feet. The ocean absorbed most of Earth's seismic energy, transforming a sudden crustal adjustment into a gentle rolling surge across thousands of miles. Scientists can now detect tsunamis by monitoring the atmosphere from space. NASA's Guardian system, which stands for GNSS Upper Atmospheric Real-Time Disaster Information and Alert Network, tracks how tsunami waves disturb the ionosphere, that electrically charged layer far above Earth's surface. When tsunami waves displace ocean water, they also push air upward, creating pressure waves that reach the ionosphere within minutes. These atmospheric disturbances slightly distort signals from GPS satellites. In September 2025, Guardian successfully detected the Kamchatka tsunami up to 45 minutes before traditional tide gauges confirmed the wave's arrival in Hawaii. This technology doesn't prevent tsunamis, but it gives coastal communities precious extra minutes to move to higher ground. Time, in disasters, is the difference between survival and tragedy. Hurricanes gain strength from warm ocean water, and our warming climate makes them more intense. A study published in 2024 found that climate change increased wind speeds for every Atlantic hurricane that formed during the 2024 season. On average, these 11 hurricanes were 3 to 14 miles per hour stronger than they would have been without human-caused ocean warming. Hurricane Helene, which reshaped western North Carolina as a tropical storm, reached peak wind speeds that were approximately 16 miles per hour more intense because of warmer ocean temperatures. Hurricane Milton rapidly intensified by 120 miles per hour in less than 36 hours over waters whose temperatures were made 400 to 800 times more likely by climate change. Warmer water fuels stronger storms, creating a clear link between rising temperatures and increasing hurricane intensity. The Pacific Ring of Fire encircles the world's largest ocean with a chain of earthquakes and volcanoes. This 25,000-mile arc follows the boundaries where the Pacific Plate meets surrounding plates. More than 80% of the world's largest earthquakes occur along this ring, as do roughly 75% of the world's active volcanoes. The ring extends from New Zealand up through Indonesia, Japan, and Russia's Kamchatka Peninsula, then down along Alaska and the western coasts of North and South America. Despite its ominous name, the Ring of Fire simply marks where Earth's crust is most actively reshaping itself. Subduction zones, where one plate slides beneath another, create both the deep earthquakes and the volcanic chains that define this region. The ring isn't a threat, it's a visible boundary of planetary transformation. Earthquakes can travel faster than the seismic waves they generate, creating what scientists call supershear earthquakes. Normally, earthquake ruptures spread along a fault at speeds slower than the shaking waves they produce. But under certain conditions, the rupture accelerates, overtaking its own seismic waves and creating a geological sonic boom. Research published in 2025 warns that many California faults capable of producing magnitude 7 earthquakes might generate these supershear events. The effect is similar to a jet breaking the sound barrier. The rupture front moves faster than the warning signals, creating intense ground motion that arrives with almost no advance notice. USC researchers studying this phenomenon found that supershear earthquakes produce ground shaking that's significantly more intense than conventional earthquakes of the same magnitude. Deep earthquakes were once considered impossible in certain stable regions, but scientists now understand how ancient faults can suddenly reactivate. Faults that have been inactive for millions of years slowly heal over time. Minerals precipitate in the fractures, essentially gluing the broken rock back together. This healing process makes the old fault zone stronger than the surrounding rock. When new stress eventually builds up, the rock breaks in a new location, or paradoxically, the healed fault breaks again because it has become a zone of weakness surrounded by strength. Research published in November 2025 revealed that faults in stable regions like Utah and the Netherlands can produce significant earthquakes despite being geologically inactive for eons. Even ancient wounds in Earth's crust can sometimes open again, given enough pressure and time. Volcanic systems beneath ice create hidden dangers and unexpected floods. Iceland's Grímsvötn volcano lies buried under the Vatnajökull glacier, Europe's largest ice cap. When magma rises beneath the ice, it melts enormous volumes of water that accumulate in subglacial lakes. Eventually, the water pressure becomes too great, and the lake bursts through the ice in what Icelanders call a jökulhlaup, a glacial outburst flood. These floods can release more water than the Amazon River, sweeping away bridges, roads, and anything else in their path. Grímsvötn last erupted in 2011, producing a massive ash plume that disrupted air travel across Europe. Right now, the ground shows signs of deformation, indicating magma continues accumulating beneath the ice. The volcano sleeps, but not deeply, and not forever. Earthquakes generate intense heat that can instantly melt rock. MIT scientists recreated earthquakes in laboratory conditions and discovered that the friction between grinding fault surfaces produces temperatures exceeding several thousand degrees Fahrenheit, hot enough to melt rock in less than a second. This helps explain mysterious glassy layers found deep in fault zones, which geologists once thought formed over much longer periods. When tectonic plates slip past each other at high speeds during an earthquake, the surfaces essentially weld together momentarily before breaking again. This flash melting releases enormous energy and may explain why some earthquakes produce more intense shaking than their magnitude would predict. The heat isn't just a side effect, it's an integral part of how Earth's crust fractures and reforms. Continents don't just split at the surface, they also peel apart from below. Research published in November 2025 revealed that when continents break apart, the process happens in two layers. The upper crust rifts and separates in the way we've long understood. But deep beneath, the continental roots actually peel away like layers of an onion, feeding volcanic activity in the surrounding oceans. Computer simulations show that slow waves in Earth's mantle strip pieces of continental crust and drag them deep into oceanic regions. This explains why some mid-ocean ridges show unexpected continental material. Earth's crust doesn't simply crack, it delaminates, with the deep layers separating on entirely different timescales than the surface. The planet transforms itself from the inside out. Subduction zones create Earth's most powerful earthquakes and violent volcanic eruptions. These are places where one tectonic plate dives beneath another, descending into the hot mantle below. As the descending plate sinks, water trapped in its rocks is squeezed out. This water rises into the overlying mantle, lowering the melting point of the rock and creating magma that eventually erupts at the surface. The Pacific Northwest sits above the Cascadia subduction zone, where the Juan de Fuca plate slides beneath North America. For the first time, scientists have directly observed this subduction zone actively breaking apart beneath the region. The plate isn't sliding smoothly, it's fracturing, a discovery that changes how researchers understand earthquake risk in Oregon, Washington, and British Columbia. earthquake faults can heal far faster than scientists once believed. Research on slow slip events in the Cascadia subduction zone revealed that some faults move repeatedly in patterns that only make sense if the fault surface heals between movements. In some cases, healing occurs within hours, rather than years or decades. This rapid healing happens because minerals in groundwater quickly precipitate in the tiny fractures, essentially gluing the fault back together. The discovery challenges long-held assumptions about earthquake cycles and recurrence intervals. If faults can heal in hours, then the time between earthquakes depends not just on how fast stress accumulates, but also on how quickly the fault can strengthen itself after each movement. The Earth repairs its own fractures with remarkable speed. Wildfires and climate change create a feedback loop that intensifies both. The 2024 wildfire season saw particularly severe fires in the Brazilian Pantanal and Amazon rainforest. Driven by climate-related droughts, these fires released enormous amounts of carbon dioxide into the atmosphere, contributing to further warming. Croatia experienced a 21% increase in wildfires in 2024 compared to the previous year. The western United States has seen 17 of California's 20 largest wildfires by acreage occur since 2000. Wildfire damage during the 2017 to 2021 period exceeded $90 billion. As temperatures rise and droughts become more frequent, forests become drier and more flammable. Each fire releases carbon that was stored in trees for decades or centuries, accelerating the warming that makes future fires more likely. Landslides reshape mountain landscapes over geological time. In mountainous regions, heavy rainfall often triggers widespread slope failures. As climate change increases the frequency of extreme rainfall, landslide risk grows accordingly. A massive landslide in Papua New Guinea's Enga province in May 2024 displaced more than 1,600 people and affected nearly 4,000. The landslide occurred in a region already experiencing ongoing geological instability. In India, monsoon-triggered landslides in 2024 were made worse by climate-altered precipitation patterns. While individual landslides seem catastrophic, they're part of how mountains erode and valleys fill. Every landslide moves rock downhill, gradually wearing away peaks and distributing sediment across lower elevations. Mountains rise through tectonic forces, then slowly disappear through gravity and rain. Volcanic tremors reveal what's happening deep underground. Scientists studying Tanzania's Oldowinyo Lengai volcano in October 2025 successfully traced tremor signals in three-dimensional space for the first time, pinpointing their exact locations within the volcanic system. These continuous rhythmic vibrations differ from earthquake shaking. They indicate moving magma or gas. By tracking where tremors originate, volcanologists can map underground magma chambers and predict where future eruptions might break through to the surface. The technique works like a medical ultrasound, using seismic waves to create images of Earth's interior. Each volcano has a unique tremor signature, a geological fingerprint that reveals its internal structure. Listening to these subtle vibrations lets scientists see into the Earth without drilling. Some volcanoes don't explode. They simply overflow. A study published in November 2025 finally explained why certain volcanoes produce gentle lava flows, while others generate violent eruptions. The answer lies not just in gas content, but in how the magma moves. Rising magma experiences shearing forces as it flows through narrow channels in the rock. This shearing motion can cause dissolved gases to form bubbles, even when pressure remains constant. If bubbles form slowly through shearing, rather than through rapid pressure drop, they grow gently and escape without explosion. The discovery helps explain why volcanoes like Hawaii's Mauna Loa produce calm lava flows, while others like Mount St. Helens explode catastrophically. The violence depends on how quickly gases can escape from the rising magma. Earth's magnetic field protects us from more than just solar radiation. It also influences volcanic activity in subtle ways. The Tonga volcano, Hunga Tonga Hunga Ha'apai, erupted in January 2022 with such force that it sent pressure waves completely around the planet multiple times. The eruption also produced a tsunami and heavy ashfall across island nations. Research into this event revealed unexpected connections between volcanic eruptions and atmospheric phenomena. The eruption was so powerful it punched through the stratosphere, injecting water vapor directly into the mesosphere, something rarely observed. The effects lingered in Earth's atmosphere for months afterward. Some eruptions are so immense they temporarily alter global atmospheric circulation patterns, demonstrating how geological events can influence the air we breathe thousands of miles away. Floods deposit nutrients that sustain agriculture for generations. The annual flooding of rivers like the Nile, Tigris, and Euphrates enabled ancient civilizations to flourish by regularly replenishing soil fertility. While modern flood control has reduced this natural fertilization, it has also contributed to soil depletion in many regions. When rivers overflow their banks, they spread sediment rich in organic matter across floodplains. This process has shaped human history. The world's first cities arose in flood-prone river valleys precisely because the periodic inundation made agriculture reliable and productive. What we now call 100-year floods were once simply part of Earth's seasonal rhythms. Disruptive to modern infrastructure, perhaps, but essential to the ecosystems and agricultural systems that evolved alongside them. Drought and flood can follow each other with surprising speed in a phenomenon called drought-to-flood abrupt alternation. Climate change is making these rapid transitions more common. China experienced an increase in these events during 2024, with some regions swinging from extreme drought to severe flooding within weeks. The transitions occur when atmospheric circulation patterns shift dramatically. Months of drought dry out soil, which then cannot absorb water when heavy rains finally arrive. The result is flash flooding, even when total rainfall isn't exceptional. Research published in 2025 shows that these whiplash transitions are becoming more frequent globally. The climate system, responding to warming, oscillates more violently between extremes. Stability gives way to unpredictability. The 2024 Atlantic hurricane season produced 18 named storms, including 11 hurricanes. 5 of these intensified into major hurricanes rated Category 3 or higher on the Saffir-Simpson scale. Attribution science, a relatively new field that quantifies how climate change affects specific weather events, found that ocean warming caused by human activity increased wind speeds for every single hurricane in 2024. The storms were, on average, 1 category stronger than they would have been without climate change. This doesn't mean climate change caused the hurricanes. Hurricanes have always formed in the Atlantic, but warmer ocean temperatures give storms more energy to draw upon, allowing them to intensify more rapidly and sustain higher wind speeds. The difference between a Category 2 and Category 3 hurricane can mean billions of dollars in damages. Rapid intensification makes hurricanes particularly dangerous because they can catch forecasters and populations off guard. Rapid intensification occurs when a hurricane's maximum sustained winds increase by at least 35 miles per hour within 24 hours. Between 1980 and 2024, 186 Atlantic hurricanes underwent rapid intensification. Nearly 1/4 of these storms experienced extreme rapid intensification, defined as wind speed increases of at least 50 miles per hour in a single day. Hurricane Milton demonstrated this phenomenon dramatically in early October 2024, strengthening from a tropical storm to a Category 5 hurricane in just over a day. Forecasting rapid intensification remains challenging despite improved technology. The National Hurricane Center has made significant progress in recent years, but the physical processes governing rapid intensification are complex and not yet fully understood. Meteor showers occasionally pose hidden risks. The torrid meteor shower, which occurs each autumn, originates from debris left behind by Comet Encke. while most meteors burn up harmlessly in the atmosphere, creating beautiful shooting stars. Research suggests that the torrid stream may contain larger fragments capable of surviving atmospheric entry. These occasional larger objects could potentially impact Earth's surface. Studies examining the torrid swarm found that certain years might bring an increased risk of impacts from meter-sized objects. The danger remains extremely low, far less than the risk from near-Earth asteroids. But it serves as a reminder that even familiar annual meteor showers contain elements of unpredictability. The universe continues to send us occasional reminders of our cosmic vulnerability. The Pacific Tsunami Warning Center, established in 1949 after a devastating tsunami killed 159 people in Hawaii, now serves as the operational headquarters for tsunami monitoring across the Pacific Ocean. The center coordinates with 46 member countries and disseminates alerts to more than 100 locations. During the July 2025 Kamchatka earthquake, the Pacific Tsunami Warning Center issued initial tsunami threat messages within minutes, facilitating evacuations in Russia, Alaska, and Hawaii. The response demonstrated decades of improvement in warning systems and international cooperation. No warning system can prevent a tsunami, but rapid alerts save lives by giving coastal communities time to move to higher ground. In disasters, seconds and minutes translate directly into survival. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside. Trillions of organisms working in silence, heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. You are a complete ecosystem, diverse, self-balancing. Just like Earth herself, constantly adjusting, constantly healing, constantly transforming. Your body understands change as growth, pressure as preparation for release. Rest in that wisdom now. Now we continue. Volcanic islands appear from underwater eruptions, building slowly from the ocean floor. The island of Surtsey emerged off Iceland's coast in 1963, growing from nothing to a landmass of nearly 1 square mile within just 4 years. Scientists watched in real time as life colonized the new land. First bacteria and fungi, then plants whose seeds arrived on winds or in bird droppings, then insects and eventually nesting birds. Home Reef Volcano in Tonga offers another example. In January 2025, scientists documented a new lava island growing in the ocean. The newly formed lava covered approximately 67,000 square meters, comprising about 42% of the island's total area. Creation happens quickly when measured against human lifetimes. Earthquake. Early warning systems can provide seconds to minutes of advance notice before strong shaking arrives. The Shake Alert system, operated by the USGS along the U.S. West Coast, detects the initial seismic waves from an earthquake and calculates its magnitude and location. Because information travels through fiber optic cables faster than seismic waves travel through rock, the system can alert people farther from the epicenter before shaking reaches them. The warning time is short, typically 5 to 20 seconds, but even seconds allow people to take protective actions. Drop, cover, and hold on. Stop surgeries in operating rooms. Slow trains. Close gas valves. The system doesn't predict earthquakes. It simply recognizes that one has started and warns those who haven't yet felt it. Storm surge causes more damage during hurricanes than wind alone. As a hurricane approaches land, it pushes ocean water toward the shore. The water has nowhere to go except up and inland. During Hurricane Helene in September 2024, storm surge inundated coastal areas of Florida, with walls of water exceeding 15 feet in some locations. Climate Central's new Risk Viewer website provides photorealistic visualizations of storm surge at specific coastal locations, helping communities understand their risk. Sea level rise amplifies storm surge. Water starts from a higher baseline, so surge reaches farther inland than it did decades ago. Rising seas essentially give hurricanes a head start on flooding coastal communities. Glacial earthquakes occur when massive chunks of ice break off from glaciers and fall into the ocean. These icebergs, some weighing millions of tons, generate seismic waves detectable on instruments thousands of miles away. Greenland and Antarctica produce dozens of these glacial earthquakes annually, and the frequency has increased as warming temperatures accelerate ice loss. The earthquakes don't cause damage. They're too small and too far from population centers, but they serve as measurable indicators of glacial retreat. Each glacial earthquake represents ice that was frozen for thousands of years, now returning to the ocean as water. The sound of cracking ice, translated into seismic waves, tells us how quickly Earth's frozen places are transforming. Soil liquefaction. During earthquakes causes buildings to sink or topple, even when the structures themselves remain intact. Water-saturated soils lose their strength when shaken, behaving temporarily like a liquid rather than solid ground. Buildings constructed on liquefied soil can tilt dramatically or settle unevenly. In the 1964 Alaska earthquake, liquefaction caused massive landslides in Anchorage, despite the earthquake's epicenter being distant. Engineers now understand which soil types are most susceptible and can take preventive measures: compacting soil, installing drainage systems, or driving deep pilings to bedrock. The ground beneath us isn't always as solid as it appears. Some soils remember that they were once water and mud. The Sahara Desert was once green grassland with rivers and lakes. Around 5,000 to 6,000 years ago, shifts in Earth's orbit changed rainfall patterns, transforming North Africa from savanna to desert. This wasn't a disaster. It was climate changing over timescales that allowed ecosystems to migrate. The Sahara has oscillated between wet and dry states multiple times over hundreds of thousands of years, driven by regular variations in Earth's tilt and orbit. These Milankovitch cycles continue today, though human-caused climate change now adds a new factor to Earth's natural variability. The Sahara will eventually turn green again, perhaps in 15,000 years. Deserts and forests trade places across geological time. Atmospheric rivers carry enormous amounts of water vapor. These narrow bands of concentrated moisture in the atmosphere flow like rivers through the sky, transporting water from tropical regions toward the poles. When an atmospheric river makes landfall on a mountain range, the moisture condenses and falls as rain or snow. California receives between 30 to 50% of its annual precipitation from just a few atmospheric river events. These events can drop more than 20 inches of rain in a single storm, causing flooding and landslides. Yet the same storms refill reservoirs and snowpack that provides water through dry summers. Too much water arrives too quickly. Coral reefs protect coastlines from storms while providing habitat for countless species. Reefs act as natural breakwaters, absorbing up to 97% of wave energy before it reaches shore. During hurricanes, areas with intact mangrove forests experience significantly less damage than areas where mangroves have been cleared. But warming ocean temperatures cause coral bleaching. The corals expel the algae they depend on for food, turning white and often dying. Once reefs die, coastlines lose their protection. The relationship creates a feedback loop. As reefs decline, storm damage increases, and as storms become more intense due to warming oceans, reef recovery becomes harder. Permafrost thawing releases methane, a potent greenhouse gas trapped in frozen soil for thousands of years. As Arctic temperatures rise, ground that has remained frozen since the last ice age begins to thaw. Organic matter in the soil decomposes, releasing both carbon dioxide and methane. Methane is roughly 25 times more effective at trapping heat than carbon dioxide over a century-long timescale. This creates another feedback loop. Warming thaws permafrost, which releases methane, which causes more warming, which thaws more permafrost. The Arctic is warming faster than any other region on Earth, making permafrost thaw a growing concern. Sinkholes form when underground water dissolves limestone bedrock. Over decades or centuries, the bedrock develops cavities. Eventually, the ceiling of a cavity collapses, creating a sinkhole at the surface. Florida is particularly prone to sinkholes because much of the state sits on limestone. Sinkholes can appear suddenly, a road or building intact one day, swallowed by a crater the next. While dramatic, sinkholes are part of how landscapes evolve. They create new wetlands and ponds, providing habitat for wildlife. In some regions, ancient sinkholes filled with sediment contain remarkable archaeological sites. What seems like destruction is actually Earth reorganizing its surface. Lightning strikes Earth roughly 100 times every second. Though most strikes hit open ground or water rather than structures or people, each lightning bolt heats the surrounding air to approximately 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. This extreme heat creates the thunder we hear as a sonic boom. Lightning ignites many wildfires, particularly in remote wilderness areas. These lightning-caused fires have historically played important roles in forest ecology, clearing underbrush and promoting certain plant species. Modern fire suppression has disrupted these natural cycles, leading to fuel accumulation that makes modern wildfires more intense. Dust storms transport nutrients across continents and oceans. Saharan dust blown across the Atlantic Ocean deposits iron and phosphorus in the Amazon rainforest, replenishing nutrients washed away by tropical rains. Without this regular dust delivery, the Amazon would be less productive. Similarly, Asian dust crosses the Pacific and deposits nutrients in Pacific Northwest forests. These transcontinental dust transfers represent essential nutrient cycles that connect Earth's deserts to its forests. What appears from human perspective as air pollution is from Earth's perspective as a nutrient distribution system. Dust clouds may reduce visibility and air quality temporarily, but they sustain ecosystems thousands of miles away. Geothermal energy harnesses Earth's internal heat, using the same volcanic processes that sometimes cause eruptions. Iceland generates nearly all its electricity and heating from geothermal sources, tapping into volcanic heat that lies close to the surface. Wells drilled into hot rock bring up steam or hot water that drives turbines or heats buildings. The technology turns volcanic regions from hazards into resources. Areas prone to earthquakes and eruptions also offer geothermal potential. The same geological activity that creates risk also provides clean, renewable energy. Earth's restless geology becomes useful when properly channeled, demonstrating how what we call disasters are simply expressions of planetary energy. The Anthropocene marks a proposed new geological epoch defined by human impact on Earth's geology and ecosystems. Future geologists studying rock layers will see distinct changes. Radioactive isotopes from nuclear testing in the 1950s. Plastic particles distributed globally. Altered sediment patterns from dam construction. Changes in fossilized pollen as humans cleared forests and planted crops. Whether natural disasters are becoming more frequent or simply affecting more people as populations grow remains debated. What's certain is that humans now influence geological processes, altering coastlines, triggering earthquakes through wastewater injection, changing atmospheric composition. We have become a geological force. Early warning systems save lives, but only when people trust them and know how to respond. After the devastating 2004 Indian Ocean tsunami, countries invested billions in tsunami warning infrastructure. Chile improved coordination between national and local agencies after its 2010 tsunami. Indonesia developed regional alert systems with international support. The social dimension matters as much as technology. Communities with strong social networks evacuate more effectively than fragmented communities, even when both receive the same warnings. Trust in authorities, regular evacuation drills, and community education determine whether warnings translate into action. The technology provides time. Human preparation determines whether that time saves lives. You're still here, still listening to Earth's secrets. That means curiosity hasn't fully rested yet, and that's okay. Take a gentle breath. Feel the weight of your body on the bed, grounded like ancient stone. We're wandering through nature's quiet wisdom together, you and I, and everyone listening in the stillness. There's no rush, no destination, just these facts drifting by like clouds. And we'll keep going, slowly. Mountain building happens so slowly that we perceive mountains as permanent. Yet the Himalayas rise approximately 1 inch per year as the Indian plate continues pushing into Asia. Over 50 million years, this collision has lifted seafloor sediments, originally deposited on an ancient ocean bottom, to elevations above 25,000 feet. Fossils of marine creatures sit embedded in rocks at the summit of Mount Everest. What is now Earth's highest point was once underwater. Mountains demonstrate Earth's patience. They don't appear suddenly. They accumulate, grain by grain, inch by inch, rising through pressures we cannot directly see. Rivers change course over centuries, abandoning old channels and carving new ones. The Mississippi River has shifted its mouth multiple times throughout history. The Huanghe in China has changed course dramatically at least 9 times in recorded history, sometimes flowing north of the Shandong Peninsula, sometimes south, each time affecting millions of people. These avulsions occur when sediment builds up in the riverbed faster than the current can carry it away. Eventually, during a flood, the river finds a steeper path. What was farmland becomes riverbed. What was river becomes farmland. Glaciers flow like very slow rivers, moving downhill under their own weight. The ice appears solid, but under pressure it deforms and flows. Glaciers in steep mountain valleys might move several feet per day. Ice sheets in Antarctica move just inches per year. As they flow, glaciers carve U-shaped valleys, pluck rocks from mountainsides, and grind bedrock into fine powder called glacial flour. This flour, suspended in meltwater, gives glacial streams their distinctive milky appearance. Glaciers are Earth's sculptors, patiently reshaping mountain landscapes over thousands of years. Sea level has changed dramatically throughout Earth's history. During ice ages, sea level drops by 300 feet or more as water becomes locked in ice sheets. Coastlines extend miles beyond their current positions. During warm periods, sea level rises, flooding coastal plains. 20,000 years ago, during the last ice age, you could walk from England to France across dry land. Today, rising seas threaten to submerge island nations within this century. Sea level changes slowly from human perspectives, but it never stops moving. Asteroid impacts have periodically reshaped life on Earth. The dinosaur extinction 66 million years ago resulted from an asteroid roughly 6 to 9 miles wide, striking what is now Mexico's Yucatan Peninsula. The impact vaporized rock, created magnitude 10 earthquakes, triggered massive tsunamis, and threw so much debris into the atmosphere that sunlight dimmed for years. Yet this catastrophe created opportunities for surviving species. Mammals, which had been small and relatively insignificant during the dinosaur era, diversified and grew larger in the aftermath. Volcanic eruptions can affect global climate. The 1815 eruption of Mount Tambora in Indonesia, one of the most powerful in recorded history, released so much ash and sulfur dioxide into the stratosphere that it cooled global temperatures. 1816 became known as the year without summer. Snow fell in New England in June. Crops failed across Europe. Famines spread. Yet the same volcanic eruptions that occasionally cool climate also release carbon dioxide. contributing to long-term warming over geological timescales. Volcanoes both cool and warm Earth, depending on what materials they release. Mangrove forests protect tropical coastlines from storms while providing habitat for countless species. Their tangled roots slow waves, trap sediment, and stabilize shorelines. During hurricanes, areas with intact mangrove forests experience significantly less damage than areas where mangroves have been cleared. Yet coastal development continues removing mangroves despite their protective value. The Philippines, which experiences some of the world's most intense typhoons, has lost approximately half its mangrove forests. What we remove for short-term gain would have protected us from nature's power. Plate tectonics operates as Earth's thermostat, regulating climate over millions of years. Subduction zones pull carbon-rich sediments deep into the mantle. Volcanoes release carbon dioxide back into the atmosphere. Mountain building exposes fresh rock that weathers and draws carbon dioxide from the air. These processes balance each other over geological timescales, maintaining conditions suitable for life. Without plate tectonics, Earth's climate would be dramatically different, perhaps frozen like Mars or hot like Venus. Our planet's restless geology makes it habitable. Deep ocean currents carry heat around the planet, influencing climate patterns far from their origins. The Great Ocean Conveyor Belt, or thermohaline circulation, moves water from the surface to the deep ocean and back again over approximately 1,000 years. Warm surface water flows north in the Atlantic, releases heat to the atmosphere, becomes dense from evaporation and cooling, then sinks and flows southward at depth. This circulation helps regulate Earth's temperature distribution. Changes to this circulation could alter climates globally. Halfway through our journey now, and perhaps you're beginning to see the pattern. What we call disasters, earthquakes, eruptions, storms, floods, are simply Earth doing what Earth does. The planet transforms itself constantly. Tectonic plates drift. Volcanoes build land. Rivers carve valleys. Storms redistribute energy and water. These processes created the world we inhabit. They continue shaping it now. From Earth's perspective, measured across millions of years, there are no disasters, only change, only transformation, only the endless patient work of becoming. Breathe slowly now and consider time itself. You are living in a single moment of geological time, a moment so brief that mountains seem eternal. Yet those mountains are rising, grain by grain. Continents are drifting, inch by inch. Everything you see is mid-transformation, frozen only by the shortness of human lifetimes. Imagine looking down on Earth from space, watching centuries pass in seconds, seeing coastlines shift, rivers wander, forests come and go like breaths. You would see that nothing stays still, everything flows. Even the ground beneath you is moving, so slowly that stillness is an illusion. Rest in that flow now. Let yourself drift with geological time. We're halfway there. Islands disappear as sea level rises. Small Pacific island nations like Tuvalu and Kiribati face existential threats from rising oceans. Some islands have already become uninhabitable as saltwater infiltrates freshwater aquifers. Communities that have lived on these islands for thousands of years must now consider relocation. The islands aren't sinking. The ocean is rising. As ice melts in Greenland and Antarctica, as warming ocean water expands, sea level climbs, islands slowly vanish, submerged by processes happening thousands of miles away. Desertification transforms grasslands into desert through a combination of climate change and land use. The Sahel region south of the Sahara Desert alternates between wet and dry phases over decades. During dry phases, overgrazing and farming stress vegetation. Without plant roots holding soil, wind erodes the topsoil. The land loses fertility. What was marginal grassland becomes desert. Yet the process can reverse. Reforestation projects in Niger have successfully restored millions of acres by protecting natural regeneration of native trees. Mudslides move slower than waterfloods, but carry immense destructive power. Unlike flooding water that eventually drains away, mudslides deposit debris that can be tens of feet deep. Entire valleys fill with mud, rock, and broken trees. Rebuilding becomes nearly impossible where mudslides have occurred. Yet these deposits, over centuries, weather into fertile soil. What buries a village today becomes farmland for future generations. The transformation takes human lifetimes to complete, requiring patience measured in decades. Tornadoes form when atmospheric conditions create rotating columns of air. The United States experiences more tornadoes than any other country due to its unique geography. Cold, dry air from Canada meets warm, moist air from the Gulf of Mexico over the flat Great Plains, creating ideal conditions for severe thunderstorms. Most tornadoes last only a few minutes and travel less than 5 miles. They carve narrow paths through the landscape, leaving destruction in strips sometimes just yards wide. Wetlands absorb floodwaters like sponges, reducing downstream flooding. When rivers overflow, wetlands expand to accommodate excess water, then slowly release it as levels drop. This natural flood control has largely been lost as wetlands were drained for agriculture and development. The Mississippi River once had extensive wetlands along its length. Now, constrained between levees, the river has nowhere to spread during floods. What we removed for farmland would have protected downstream cities. Barrier islands protect mainland coastlines from ocean waves and storms. These narrow islands form from sand deposited by currents and waves. They migrate landward naturally as sea level rises, maintaining their position relative to the coast. Development on barrier islands disrupts this natural migration. Buildings anchor the sand in place, preventing the island from moving. Eventually, rising seas overwhelm fixed barriers. The islands would survive if allowed to migrate, but human structures force them to drown. Groundwater depletion causes land to subside. In California's Central Valley, excessive pumping of groundwater for irrigation caused the land surface to drop more than 30 feet in some areas. Once the ground compacts, the change is permanent. The underground spaces that held water collapse and cannot expand again. Mexico City sinks several inches per year as groundwater is extracted faster than rain can replenish it. The city's colonial-era buildings tilt and crack as foundations settle unevenly. Auroras appear when solar wind particles interact with Earth's magnetic field and atmosphere. These dancing lights typically occur near the poles, but severe solar storms can push auroras to lower latitudes. The same solar activity that creates beautiful auroras can disrupt power grids, damage satellites, and interfere with radio communications. Our technological civilization has made us vulnerable to space weather. The sun's activity follows an 11-year cycle, with stronger storms during solar maximum. Droughts develop slowly, worsening week by week until rivers dry and crops fail. Unlike sudden disasters, droughts give warning but offer no clear end point. The Dust Bowl of the 1930s resulted from a combination of drought and poor farming practices. Topsoil, dried and loosened, blew away in massive dust storms. Farmers abandoned millions of acres. The drought eventually ended, but the damaged land took decades to recover. Heat waves kill more people than any other weather disaster in the United States, though deaths are often undercounted. Coroners typically attribute deaths to direct causes like heart failure rather than heat stress. July 22nd, 2024 was Earth's hottest day on record. Nearly half of all people on the planet experienced dangerous temperatures that day, made at least 3 times more likely by climate change. Extreme heat is invisible, making it easier to ignore. Peat bogs store enormous amounts of carbon accumulated over thousands of years. When drained for agriculture or development, peat peat oxidizes and releases this stored carbon. Indonesia's peat fires in 2015 released more carbon dioxide daily than the entire United States economy. The fires smoldered for months, burning underground through dried peat. Smoke blanketed Southeast Asia. Restoring and protecting peat bogs helps stabilize climate by keeping carbon stored underground. Sand dunes migrate across deserts, driven by wind. They move slowly, perhaps 30 to 60 feet per year, but they move nonetheless. Communities on the edges of deserts sometimes find dunes encroaching on farmland and villages. The Sahara Desert expands and contracts over decades and centuries, responding to variations in rainfall. What is desert today was savanna yesterday, and may be savanna again tomorrow, if we measure time in thousands of years. Ice ages have come and gone throughout Earth's history, each lasting tens of thousands of years. The most recent ice age peaked 20,000 years ago. Ice sheets up to 2 miles thick covered Canada, Scandinavia, and parts of northern Europe and Asia. Sea level was 300 feet lower. Then Earth warmed, ice melted, and sea level rose. We currently live in an interglacial period, a warm interval between ice ages. Monsoons are seasonal wind patterns that bring wet and dry seasons to tropical regions. The Indian monsoon provides the majority of annual rainfall for more than 1 billion people. When the monsoon is delayed or weak, drought threatens agriculture. When monsoon rains are especially heavy, flooding inundates farmland and cities. Climate change appears to be making monsoons less predictable, with longer dry periods followed by more intense rainfall. Cave systems form as slightly acidic rainwater dissolves limestone over millions of years. Underground rivers carve passages through the rock. Some caves contain formations, stalactites, stalagmites, flowstone, that grew drop by drop over thousands of years. These caves preserve climate records in their formations, recording ancient rainfall patterns in chemical signatures. When sinkholes suddenly appear at the surface, they often reveal caves that have existed underground for ages. Forests regulate local rainfall through transpiration. Trees pull water from soil and release it through their leaves. This moisture rises and forms clouds, which produce rain. Clearing forests disrupts this cycle, reducing rainfall. The Amazon rainforest creates much of its own rain through this process. Deforestation in one part of the Amazon can reduce rainfall hundreds of miles away. The forest and the rain depend on each other. Earthquakes change Earth's rotation slightly by redistributing mass. The 2011 Japan earthquake shortened Earth's day by about 1.8 microseconds by altering how mass is distributed around the planet. The effect is too small for anyone to notice, but sensitive instruments can measure it. Large earthquakes also shift Earth's axis of rotation by a few inches. The planet adjusts to these changes seamlessly. Lightning can create glass when it strikes sand. The intense heat, 50,000 degrees, melts sand into hollow tubes called fulgurites. These glassy formations preserve the lightning's path underground. Some fulgurites extend several feet into the soil. They're fragile and rare, forming a geological record of atmospheric electricity. Ancient fulgurites found in sand deposits reveal that lightning has been striking Earth for as long as there have been storms. Erosion shapes all landscapes eventually. Mountains rise through tectonic forces. Then erosion tears them down. Wind, water, ice, and gravity all work constantly to smooth Earth's surface. The Appalachian Mountains were once as tall as the Himalayas, but have been eroding for hundreds of millions of years. What is high becomes low. What is low fills with sediment. Earth's surface constantly redistributes itself. River deltas grow where sediment accumulates faster than currents and waves can remove it. The Mississippi Delta, the Nile Delta, the Ganges Delta, each formed from millennia of sediment deposition. These deltas sink naturally under their own weight, balanced by new sediment arriving from upstream. Dams upstream trap sediment, stopping the replenishment. Deltas stop growing and begin sinking beneath rising seas, threatening millions who live there. Volcanoes create fertile soil through weathering of volcanic rock. Basalt lava weathers into clay-rich soil full of minerals that plants need. Some of the world's most productive agricultural regions sit on volcanic soil despite the risk of future eruptions. Java, with its many active volcanoes, supports high population density because the volcanic soil is exceptionally fertile. Risk and fertility coexist. Earthquakes release energy that accumulated over decades or centuries. The energy doesn't disappear. It converts from potential energy stored in bent rock to kinetic energy released as seismic waves. These waves radiate outward, shaking the ground, then dissipate as heat. The process is efficient and inevitable. Stress builds, friction holds, eventually friction fails. The earth moves, energy releases, equilibrium returns temporarily. Clouds form when air rises, expands, and cools until water vapor condenses into droplets. The process is simple, but creates endless variety. Cumulus, stratus, cirrus, nimbus. Each cloud type forms under specific conditions. Thunderstorm clouds tower miles high. Fog is simply a cloud touching the ground. All clouds are water waiting to return to Earth, completing the cycle that lifted them. Fossils preserve evidence of ancient disasters. Layers of iridium in rock mark the asteroid impact that ended the dinosaur era. Ash layers record volcanic eruptions that occurred millions of years ago. Fossilized ripples show where tsunamis washed inland, depositing sand far from any beach. Earth keeps records of its violence. Each layer of rock tells a story, if you know how to read it. The Earth continues transforming, as it has for 4.5 billion years. Continents drift, mountains rise and erode, oceans open and close, ice ages come and go. Through it all, life adapts, species evolve, ecosystems shift. What we perceive as disasters are moments in an ongoing transformation that never stops, never pauses, never reaches a final form. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Earth orbits the sun. The moon orbits Earth. Tides rise and fall. Seasons turn. All are circles, cycles, endless rhythms. Like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe of cycles. Mountains rise and erode. Forests grow and burn and grow again. Rivers flood and recede. Ice advances and retreats. You are also part of these eternal movements. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits. Unhurried, unresisting, simply existing. Rest in these cycles now. They continue without your attention. They'll continue after you drift away. Almost there. Perhaps now you begin to understand. Natural disasters aren't interruptions to Earth's normal state. They are Earth's normal state. The planet is always moving, always changing, always releasing energy. We call certain moments disasters only because they intersect with human timescales and human places. From Earth's longer perspective, there is only transformation. Destruction creates space for new growth. Forest fires clear undergrowth, allowing sunlight to reach the soil. Floods deposit nutrients on farmland. Volcanoes build islands. Earthquakes release pressure that would otherwise keep building. What seems like endings are also beginnings. The land transforms, and life adapts to the transformed landscape. Rivers carve canyons over millions of years, one grain of sediment at a time. The Grand Canyon reveals 2 billion years of Earth's history in exposed rock layers. The Colorado River didn't suddenly create this wonder. It patiently wore away the rock, working steadily for perhaps 6 million years. Patience on geological timescales achieves what force cannot. Mountains remember their birth in folded rock layers. The Appalachians formed when continents collided 300 million years ago. The rock layers buckled and warped like rumpled fabric. Now, after eons of erosion, we can read this ancient collision in the mountain's stone. Every landscape tells the story of its formation. Glaciers retreat and advance in rhythm with Earth's climate cycles. Ice that accumulated over thousands of years melts in decades. The glaciers don't disappear. They transform from ice to water, continuing their journey differently. The water flows to the ocean, raising sea level slightly, contributing to the planetary circulation that moves heat around the globe. Coastlines are temporary boundaries between land and sea. Beaches shift with seasons and storms. Barrier islands migrate. Deltas extend then retreat. The line between land and water has never been fixed. It flows back and forth across the centuries, responding to changing sea levels and sediment supply. Soil forms so slowly that it's essentially non-renewable on human timescales. It takes roughly 500 years to build 1 inch of topsoil from rock and organic matter. Yet that same inch can erode in a single season if vegetation is removed. Soil connects living and non-living worlds. Water cycles through Earth's systems, ocean to atmosphere, to land, to river, to ocean again. The same water molecules have circulated for billions of years. Rain that falls today might have fallen on dinosaurs, or evaporated from ancient oceans, or been locked in ice for millennia. Tectonic plates move at roughly 2 inches per year. This seems impossibly slow until you realize that over 100 million years, continents can travel thousands of miles. The Atlantic Ocean opened at this gradual pace, splitting apart what was once a single landmass. Sunlight drives Earth's weather by heating the surface unevenly. Warm air rises, creating areas of low pressure. Cool air sinks, creating high pressure. Air flows from high to low pressure, creating wind. All storms, from gentle breezes to hurricanes, follow from this simple principle. Life has survived every disaster Earth has produced over 3.5 billion years. Mass extinctions cleared the stage for new forms. Ice ages came and went. Asteroid impacts, supervolcanoes, climate changes. Life adapted, evolved, persisted. Disasters test life but don't end it. Rocks remember stress through fracture patterns and crystal alignment. Geologists read these patterns like archaeologists read pottery shards. The stones reveal their history, where pressure came from, how hot they became, how deeply they were buried, how long they resisted before breaking. Earth's atmosphere is thin, just a few miles of breathable air above a planet 8,000 miles in diameter. Yet this thin layer moderates temperature, blocks harmful radiation, and makes life possible. The atmosphere connects surface to space, Earth to sky. Seasons exist because Earth tilts on its axis. As Earth orbits the Sun, different hemispheres tilt toward the light. Summer and winter alternate north and south. This simple tilt creates the rhythm of planting and harvest, growth and dormancy, that shapes life. Gravity holds everything together, planets to stars, moons to planets, atmosphere to surface. The same force that makes objects fall also keeps Earth in orbit and creates tides. Gravity is patient, constant, inescapable. Everything eventually moves downward toward equilibrium. Ocean currents move heat from equator toward poles. Without these currents, tropical regions would be unbearably hot and polar regions even colder. The ocean moderates Earth's temperature extremes, making the planet more hospitable for life everywhere. Weathering breaks down rocks slowly but completely. Water seeps into cracks, freezes, expands, splits the rock. Roots grow in cracks, forcing them wider. Eventually cliffs crumble, boulders split, mountains become pebbles, pebbles become sand, sand becomes clay. Coral reefs grow slowly, each tiny polyp building on the skeletons of previous generations. Over thousands of years, these accumulations create massive structures visible from space. Reefs rise from the ocean floor 1 millimeter at a time. Lightning and rain together return nitrogen from the atmosphere to soil where plants can use it. Thunderstorms perform essential chemistry, converting nitrogen gas into nitrates. Each storm fertilizes the earth below through electrical discharge and rainfall. Earth has been reshaping itself for 4.5 billion years. What we witness in our brief lifetimes is one moment in an ongoing transformation. The process continues whether we observe it or not. So, could natural disasters change how we understand Earth? They already have. We see now that destruction and creation are the same process viewed at different speeds. What crumbles feeds what grows. Earth doesn't have disasters. Earth has processes. Only humans have disasters because we build permanent structures on an impermanent planet. The mismatch creates the suffering we call catastrophe. Perhaps the deepest lesson is acceptance. Earth changes, always has, always will. We can resist this truth or flow with it. Either way, the mountains will rise and erode. What we call stability is just change happening slowly enough that we don't notice. The ground beneath your feet is moving. You are moving with it, so it feels still. The real change isn't in Earth, it's in how we see. When we understand geological time, disasters become patient transformations. Chaos becomes slow artistry. Fear becomes wonder. And we rest easier. And so, our quiet journey through Earth's transformations comes to a gentle close. We've traveled from tectonic plates grinding beneath oceans to hurricanes drawing energy from warming seas, discovering along the way that what we call disaster is simply Earth doing what it has always done. From earthquakes releasing ancient pressure to volcanoes building new islands, we've glimpsed how destruction and creation flow together. The planet transforms itself patiently, grain by grain, inch by inch, across timescales that make human lifetimes seem like heartbeats. Earth's restless geology reminds us that change is the only constant. Much of the planet's most important work happens invisibly, slowly, beneath the surface, in timescales beyond human perception. These forces teach us patience. Without plate tectonics, Earth would be a dead world. The same processes that sometimes frighten us make life possible. By pausing to notice, we glimpse the extraordinary patience in ordinary stone. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about how water cycles through clouds, rivers, oceans, and rain. Everything is connected. Everything returns. Everything flows. You are part of that flow, that cycle, that eternal return. Imagine yourself dissolving into these natural rhythms, your breathing matching the tide's rhythm, your heartbeat echoing Earth's deeper pulse. No boundaries left between you and rest, between waking and sleep, between stone and water and air. Let your entire being dissolve into the rhythm of nature, into the breath of the earth, into stillness. Prepare for deep sleep now, no resistance, only peace. If these calm stories from Earth helped you breathe a little easier, passing them along could help another tired soul drift into rest. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of earthquakes and eruptions to fade now, like morning mist burning away in sunlight, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gentle gravity is pulling you softly into rest. If sleep comes, let it carry you like a river flowing inevitably toward the ocean, smoothly, effortlessly, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the plates will still be drifting. Volcanoes will still be breathing. Rivers will still be carving their patient paths. But tonight belongs to stillness. Rest well, gentle scientist, and remember, Earth transforms itself through what we call disasters, and you transform yourself through rest. Both are necessary, both are natural, both are beautiful. Fall asleep to gentle facts. Dream deeper with bedtime science. Good night.